Laser ablation deposition. Sure, I'd be happy to explain laser ablation deposition, and how it can be used to create polymer films. LAD is a process where a laser beam is used to ablate a polymer target, which creates a plasma of polymer particles that is then deposited onto a substrate to form a thin film. The plasma is formed when the laser beam hits the polymer target, causing the material to vaporize and form a cloud of polymer particles that then condenses onto the substrate. LAD has several advantages over other methods of polymer film deposition, such as spin coating or chemical vapor deposition. It is a non-contact and highly precise method that can produce films with controlled thickness and good uniformity. Additionally, LAD can be used to deposit a wide range of polymers, including biocompatible and biodegradable polymers, which makes it useful for a variety of applications such as biomedical devices, microelectronics, and optoelectronics. To create a polymer film using LAD, a polymer target is placed in a vacuum chamber, and a laser beam is focused onto the target. The laser beam vaporizes the polymer material, creating a plasma of polymer particles that is then deposited onto a substrate. The substrate is typically placed at a distance from the target, which allows the plasma to cool and condense onto the substrate as a thin film. The thickness and pattern of the polymer film can be controlled by adjusting the laser parameters, such as laser energy and pulse duration. Additionally, LAD can be used to create films with varying thicknesses and patterns, depending on the specific application. The properties of the polymer film can also be tuned by adjusting the composition of the polymer target or by using a combination of different polymer targets. Overall, LAD is a versatile and precise method for polymer film deposition that has potential applications in a variety of fields. It offers several advantages over other deposition techniques, including the ability to deposit a wide range of polymers, create films with controlled thickness and good uniformity, and produce films with specific patterns and properties. I'm interested in including biocompatible and biodegradable polymers, which makes it useful for a variety of applications such as biomedical devices, microelectronics, and optoelectronics. Yes, that's correct. LAD has the ability to deposit a wide range of polymers, including biocompatible and biodegradable polymers, which makes it useful for a variety of applications such as biomedical devices, microelectronics, and optoelectronics. For example, biocompatible polymers such as polylactic co-glycolic acid, PLGA, and polyethylene glycol, PEG, can be used for drug delivery systems or tissue engineering applications. LAD can be used to deposit these polymers onto a substrate to create thin films with precise control over thickness and uniformity, which is critical for biomedical applications. Similarly, biodegradable polymers such as polylactic acid, PLA, and polycaprolactone, PCl, can be used for tissue engineering or drug delivery applications. LAD can be used to deposit these polymers as thin films onto a substrate, which can be used as scaffolds for tissue engineering or as drug delivery platforms. In addition, LAD can be used to deposit polymers onto microelectronic and optoelectronic devices, where precise control over film thickness and uniformity is critical for device performance. For example, LAD can be used to deposit polymers onto microelectronic circuits or optical waveguides to modify their properties or to create protective coatings. Overall, the ability of LAD to deposit a wide range of polymers with precise control over film thickness and uniformity makes it a versatile technique with potential applications in a variety of fields, including biomedicine, microelectronics, and optoelectronics. Show me the chemical formula for polylactic co-glycolic acid, PLGA, and polyethylene glycol, PEG. The chemical formula for polylactic co-glycolic acid PLGA is C3H4O2NC2H2O2M, where N and M are the number of repeating units of lactic acid and glycolic acid, respectively. PLGA is a copolymer of lactic acid and glycolic acid. The chemical formula for polyethylene glycol, PG, is H-O-CH2-CH2, N-O, where N is the number of repeating units. PEG is a linear polymer composed of repeating units of ethylene oxide, which gives it its hydrophilic properties. Polylactic acid, PLA, and polycaprolactone, PCl. The chemical formula for polylactic acid PLA is C3H4O2N, where N is the number of repeating units of lactic acid. PLA is a biodegradable polymer that is commonly used in biomedical applications. The chemical formula for polycaprolactone, PCl, is C6H10O2N, where N is the number of repeating units of caprolactone. PCl is another biodegradable polymer that has a low melting point and is commonly used in applications such as drug delivery, tissue engineering, and 3D printing. I am sure you have more to add. Sure, here are some additional information about PLA and PCl. PLA is a polyester that can be derived from renewable resources such as cornstarch, sugarcane, and potato starch. It is a versatile polymer that can be synthesized with different ratios of L-lactic acid and D-lactic acid, which affects its properties such as degradation rate, crystallinity, and mechanical strength. PLA has a glass transition temperature, TG, of around 60 to 65 degrees Celsius, which means it is relatively rigid at room temperature but becomes more flexible at higher temperatures. It has a melting temperature, TM, of around 150 to 160 degrees Celsius, which makes it suitable for applications that require heat resistance. PCl is a polyester that is derived from the cyclic ester caprolactone. It is a semi-crystalline polymer that has a low melting point of around 60 degrees Celsius, which makes it easy to process using techniques such as injection molding and electrospinning. PCl has a slow degradation rate compared to PLA, which makes it suitable for long-term implantable devices such as vascular grafts and nerve regeneration scaffolds. However, this also means that it may persist in the environment for longer periods of time. PCl is a hydrophobic polymer, which means it is not easily wetted by water or other polar solvents. This property can be advantageous in some applications such as drug delivery, where it can provide sustained release of hydrophobic drugs. However, it can also limit its biocompatibility in some contexts. Explain more. PCl is a polyester that is derived from the cyclic ester caprolactone. It is a semi-crystalline polymer that has a low melting point of around 60 degrees Celsius, which makes it easy to process using techniques such as injection molding and electrospinning. PCl is a type of polyester that is derived from the cyclic ester caprolactone, which is a six-membered ring that contains an ester functional group. Caprolactone can be polymerized using a variety of methods, such as ring opening polymerization, ROP, to produce PCl. PCl is a semi-crystalline polymer, which means that it has regions of ordered crystalline structure as well as regions of amorphous structure. The degree of crystallinity in PCl can vary depending on factors such as molecular weight, processing conditions, and cooling rate during solidification. Generally, higher molecular weight PCl tends to have a higher degree of crystallinity, which can affect its mechanical properties such as stiffness and strength. One of the advantages of PCl is its low melting point of around 60 degrees Celsius, which makes it easy to process using a variety of techniques such as injection molding and electrospinning. Injection molding is a process in which molten polymer is injected into a mold and allowed to cool and solidify into a desired shape. PCl's low melting point makes it easy to melt and mold into complex shapes. Electrospinning is a process in which a high voltage is applied to a polymer solution to create a fine jet that is rapidly solidified into nanofibers. PCl's low melting point makes it easy to dissolve and process into a suitable electrospinning solution. Another advantage of PCl is its biodegradability. PCL degrades relatively slowly in the body compared to other biodegradable polymers such as PLA, which can make it suitable for long-term implantable devices such as drug delivery systems and tissue engineering scaffolds. However, the rate of degradation can be tuned by adjusting the molecular weight and crystallinity of the polymer. Overall, PCL is a versatile and useful polymer with a range of potential applications in fields such as biomedicine, materials science, and 3D printing. Like, comment, subscribe, to follow along for the trip.